Okay, two things today. Number one, we're going to talk about how to determine whether or not a function is increasing or decreasing. And it's as simple as it sounds. But more importantly, we're going to deal with something called the first derivative test. So one of the questions we haven't been able to answer yet, or we've answered sloppily, is, oh yeah, here's a critical number. So it's either a max or a min, but we haven't been able to easily figure out if it's a max or a min. So we'll get that today, which will make our lives a lot easier. Okay, it's just another component to throw into the calculations that we're working with. All right, so we'll talk about increasing and decreasing. If I showed you a picture of a graph, do you think you could tell me where it's increasing and decreasing? What does that mean? What's that? If I showed a graph to a fourth grader, do you think they'd be able to tell me where it's increasing and decreasing? Yeah. So you can do the same? Yeah. Excellent. You're smart as fourth grade. Fourth grade or fifth grade? What's the show? Fifth grader. We'll talk about the first derivative test, and today you should compliment two strangers. Okay. Don't look around at your table. You should know everybody sitting at your table. Two strangers.
Oh, a stranger.
A stranger. Stranger. Okay, here we go. There's the calculus speak. Give you a second to read that, and then give you a minute to explain it to me.
Okay.
That's great. Ben, can you explain that? Yes, a function is increasing on the interval if for any two numbers, x1 and x... Not what I'm looking for. Ben. You, Ben. No, hold on. I'm going to ask you a different question. If I give you a picture of a graph, okay, let me give you a picture of a graph. We'll stay with the standard old cubic. Okay. Come here. This will be easier if you just come up. Do you have a color preference other than red?
No.
All right, blue. Could you mark on the graph where that function is increasing?
Like this segment and that segment. And it's decreasing.
So color it, so trace the graph. There you go. So that's increasing, and then change colors.
Decreasing?
Yeah. Okay, perfect. Everybody agree?
Yeah.
Thank you. You can sit down. Why? Ben?
Slopes positive and negative.
The slopes.
Or the slopes in those two segments.
Be more specific. The slopes of what?
Line of the equation.
Which line? Because there's no lines up there. That's a cubic, right?
The cubic.
Hold on.
The slope of the tangent lines is positive.
The slope of the tangent lines are positive? Is that what you meant? Or did you mean the slope of the actual function? Oh, now we confused it.
The slope of the actual function.
The slope of the actual function. So let's suppose this function were x cubed minus 2x. How would you find the slope of the function?
Take the derivative.
So then we do want the slope of the tangent.
The tangent.
Okay, I just want to make sure that, I thought that's what you were talking about, I just want to make sure that that's where you were at. So you're saying it's increasing if the slope of the tangent line is positive, and it's decreasing?
Yeah.
Okay, good. You're just going to choose not to answer that second part? Dot, dot, dot.
I was kind of trying to see if it made sense always, but I don't think so.
How do you think a fourth grader would explain the blue stuff? Why would a fourth grader, how would a fourth grader explain that the blue is part of the graph that's increasing? It's going up. And the yellow part is decreasing because it's going down. That's what that says. So we take 2 points, x1 and x2. Where are they? They're somewhere on the graph. Let's put x1 right here. This yellow is horrible. Purple. We'll put x1 right here. We'll put x2 right here. Okay. So there's our increasing. x1 is less than x2. If x1 is less than x2, then f of x1 is less than f of x2. By the way, what's the common, how would an algebra 1 student interpret f of x1? What is that? It's a y value, right. So y value for x1 is less than the y value of x2. So we can take a big complicated calculus approach to this, but we can also just take a fourth grader approach and say, if it's going up, it's increasing. If it's going down, it's decreasing. Now, how are we going to do that from a calculus standpoint? Well, Kaylee pretty much already explained it. Take the derivative, figure out where the derivative is positive, and figure out where the derivative is negative. What if the derivative is equal to 0? Horizontal slope, which would imply that's what we call circular logic. If it's 0, then the tangent line is 0, or is horizontal. What am I saying? Now you got me confused. If the derivative is 0, then the tangent line is horizontal, which means what? Good. Maximum. So what happens as we progress through chapter 3 is we get more and more puzzle pieces till eventually they fit together, and we're going to use this information not only to do some calculus, but also we're going to be drawing graphs of functions without the use of calculator or decimals or something like that, beyond what you did last year in pre-calculus. That graph is exactly what Kaylee explained earlier. If the derivative is greater than 0, it's increasing. If the derivative is less than 0, it's decreasing. And if it's equal to 0, it's a constant, which means we have a horizontal tangent line, which, as we said, is a relative max or a relative min. Okay, so let's see this in action. I've got a cubic, strangely enough, and I'd like to know where that function is increasing and decreasing. So we're going to, instead of graphing it and using different colors like we did before, we're going to do the actual calculus. I'm going to find the critical numbers, because the critical numbers will tell me where the maxes and the mins are. Okay, so go ahead, find the critical numbers, please. Would you like a cookie or some chips? Bourbon barbecue. Bourbon barbecue. That's what it says.
We'll get drunk on Tuesday. Car, huh?
No. You said it, not me. There's also some pumpkin cookies if you'd like a chaser. Critical numbers, where are they? 0 and 1. Isn't that boring? Let's see. F prime of x is equal to 3x squared minus 3x. So 3, oh, look at that, 0 and 1. So it equals 0. Critical numbers at 0 and 1. Okay, so what happens at 0 and what happens at 1? Or I should say, what probably happens at 0 and what probably happens at 1. Yes.
Oh no, I'll just say 0. It's a relative min, and 1 is relative max.
Right. Or it could be the other way around, or they could be both, but it's going to be a max or a min.
Yeah,
Both of
would
them.
it be actually?
Not for a cubic. No, because we don't have an interval. Okay? And then, all the other stuff is either increasing and decreasing, similar to the problem we did with Ben earlier. How are we going to figure out what's what? Well, we're going to get it organized a little bit on a number line. This is called the first derivative number line. So I'm going to start with a number line, label it f prime. It seems silly to label it f prime, but that's a habit you want to get into for a couple of reasons. Later on, we're going to have second derivative number lines. And you want to keep track of exactly what we're talking about. Then put your critical numbers on that number line. This also seems like a silly statement, but put them in the correct numerical order. Right? It happens all the time. Now, are you going to screw up 0 and 1? No, but when we get into some weird square roots, square root of 3 over 2. Does anybody have any idea how big square root of 3 over 2 is?
No.
Is it bigger or smaller than 1? How do you know, Tim?
Because the root of 1.5 is probably like 0.75 or something.
Wait, what?
Square root of 3 over 2, not the square root of 3 halves,
Oh,
like on the unit circle.
That would be...
No.
Because square root of 3 is bigger than 1, over 2 is
The square root over 3 is smaller than square root over 4, which is 2 over 2. It's smaller.
Okay, so that was a long-winded way of saying, put them in the right order on the number. Now what we're going to do is test regions. Now, one of the reasons that we put f prime at the end of that number line is, number one, to identify it as a first derivative number line, but also to explain where am I plugging numbers in. So we're literally going to plug and chug here. What's a good number to pick over here? -1 works just great. Could you do -1 billion? Yeah, it doesn't matter. What are we plugging that number into? We're plugging it into f prime. That's why it says f prime there. So if I go, I can't go back because I wrote it. F prime was equal to 3x times x minus 1? Minus 1 or plus 1? Minus 1. The only thing I care about is whether the value is positive or negative. I don't care how big or small it is. And notice I've got two things multiplied together. I've got 3x times x minus 1. So what you want to ask yourself is, if I plug -1 into those two things, am I going to get a positive or negative value? So for instance, -1 times 3 is a negative answer. -1 minus 1 is a negative answer. A negative times a negative is positive, so that region is positive. What's a good number to pick in the second region? 1/2 works great. Positive value, positive times negative is negative. And then to the right of 1, 2 would be fine. Positive times a positive gives you positive. We're going to learn eventually that that simple first derivative number line contains a ton of information. Right now, all we're concerned about is increasing and decreasing. So looking at that, where's the function increasing? Good. Would you include brackets or parentheses at 0 and 1?
It's not going up or down. That's 0.
So you're saying parentheses?
Yeah, it's the
Okay.
value is 0, which is not positive.
Everybody agree? Or would you put brackets at 0 and 1? Do you like brackets? What's your argument for using brackets?
It's a critical number, so that is the exponent there, it's just the slope. Yeah, they have a lot, they have a value, which is critical number, so it's like where it's the slope is changing.
Okay, you're not going to like this. You put 100 calculus teachers in a room, they'll argue about this for 3 days. Whether or not those should be parentheses or brackets. I always use parentheses. You could use either one. Okay, so pick whatever you want. Remember though, you can't use brackets on infinity and negative infinity. That's always parentheses regardless of what we're talking about. Okay, any question?
I use brackets on one and parentheses on another.
Sure.
Alright.
That's what you want to do. It's America. But it follows. That's your version of sticking it to the man, right?
Yeah.
Okay, good. I like it. I like it. Well, now wait a second, hold on. Now I think about it, you're contradicting yourself then, right? Because one of them you're saying, I don't want to include this point because it's a max or a min, but then in the very next interval you're saying, oh yeah, it's a max or a min, so I'm going to include it.
Yeah.
I would take it for a test drive, see what happens. Worst that could happen is you get it wrong, right?
Right.
Okay. Anything difficult about this system or about this process? Okay, good. We still haven't answered one simple question, and that is, how do I determine if these critical numbers are maxes or mins, shy of graphing it, which we want to try to avoid, especially early on. Okay, that did that. To do that, we're going to use the first derivative test. The first derivative test is really simple. There's the picture of our graph, and you'll see that at 0 we have a relative max, and at 2, or 1, sorry, the scale is off, we have a relative min. How would I know that from that? How would that first derivative number line tell me that there's a relative max at 0 and a min at 1?
Well, I mean, the arrows kind of show you, but if you're going up and then down, there's going to have to be a hill, and if you're going down to up, there's going to have to be a valley.
Does that make sense to everybody? Okay, good. I don't want to beat a dead horse here, because it seems intuitively logical. Like she said, if you're going up, then going down, you must have hit the top at some point, and if you're going down, then up, you must be hitting the bottom at some point. And I like the first thing you said, too, is, well, you kind of see it from the graph. Okay, it goes up and comes down, it kind of gives you the general shape of the graph we're talking about. That's what the first derivative test says. Okay, there it is in fancy calculus speak, which is exactly what you said. But notice the first line there. I'm going to keep stressing this because people forget. Critical numbers come from where the derivative is equal to 0 and where the derivative is undefined. We're going to focus mainly on I and II. III takes care of the weird situations that come up where it's not a local extreme. Question?
Oh, if when you're determining if the critical number is max or min, can you point that to the original equation and see which one's bigger, which one that is bigger?
For an absolute max or min, yes, but for relative max or min, no. Because you could still, if you think about a function that's got a bunch of hills on it, you could have a hill, one hill higher than the other hill, and this could still be a relative max. It's just in a different region of the function. Okay. That's exactly what Amanda said. If it goes up, then comes down, it's a max. If it goes down, then comes up, it's a min. Okay, so let's do this one together. Staying with the cubic again, because the derivative's easy, we're going to take this from the start. F prime of x is equal to 3x squared plus 2x minus 5. Set that equal to 0. 3x, I hope this factors. Is that right? Yeah. X equals 2 and negative 5/3. Question?
It's not
Right, because 5 times negative 2 is not negative 5. This should be a 1. Good catch. I teach calculus. Is that better? Good. Okay, so those are my critical numbers. And because it's a polynomial, I have no points that are undefined, so I'm good to go. Slap that on a first derivative number line. Okay, which one is this? Negative 5/3 or 1? Good, just checking. What's a good number to pick out here on the left? Negative 2? Okay, so I put negative 2 in here. Do I get a positive or a negative value? Negative. If I put a -2 in here, do I get a positive or negative? Negative times a negative is positive. Therefore, it's increasing in there. What's a good number in here to pick? 0 works nice. 5 times -1 is negative. Decreasing. Let's put a big honking number in there. 1 gabillion. If I put in 1 gabillion, do I get a positive or a negative value? Positive. Okay, the next thing I'll warn you is that what people end up doing is they start to see patterns develop, and so they figure, okay, if I test one region, then it's got to flip back and forth between up, down, up, down, up, down. That doesn't always happen. You got to test each region. Okay? So what does that tell me? What does that little graph in the lower right-hand corner of the screen tell me? There's a number of things. Nolan.
It tells you the intervals of the graphs increasing and decreasing.
With parentheses or brackets? Or one of each? Just personal choice. Parentheses. Okay, good. Anything else? Good.
Tells us the relative max and -5/3, relative min at 1.
Max at -5/3, min at 1. Beautiful. Anything else? That's about it. Okay. So, any problems there? One last thing. Well, a couple last things, but before I move on to the next problem, I do want to mention that the College Board, people that give you the AP test, they're really big on mathematicians using sentences. So when you do a problem like this, they're going to require that you summarize it with a sentence, and those sentences should look something like that. That sentence tells the reader, aka the grader, that you know exactly what you're talking about. Relative min occurs at that x value because f prime changes from negative to positive. A relative max occurs at x equals -5/3 because f prime changes from positive to negative. You will need to use those types of sentences to explain those maxes and mins. Right? Good? You have those? Yes or no? Okay, good. Do that one on your own. Include your sentences. Okay, stop what you're doing for a second. Quick procedural question. How many of you are doing product rule? Raise your hand. Did anybody think to multiply that out? Okay. By the way, for those of you that multiplied it out, what's x to the 1/3 times -x? Sorry. Good, just checking to make sure you're good to go.
Since you're multiplying, it's still negative. Wait, what? We're talking about what is 1/3? One.
What's negative? So then what is it? Oh, no, you can't because it's the
Took out 4 characters.
the 8 from top?
Yeah, that's right.
But then minus. Wait, I have C over 3x and then negative. No, I'm saying this will be the next thing. Oh, the 8 goes into that.
I got 2x plus 8 over 3x.
No, I'm saying it would be like straight up.
All right, the bell's gonna ring in a minute, so here's what we'll do. You should have, this is actually the last slide on the slideshow. So we'll start tomorrow by having somebody put that problem up on the board. There's 2 components of this problem that are important. Wait, stop backing up for a second. Number 1 is actually doing and grinding out the derivative and being able to find the critical numbers. The second part is being able to use the first derivative test for what we did today. The first derivative test on this problem is actually the easy part. It's the derivative and the critical numbers that are difficult. We'll start with that tomorrow. You should have enough information though to do day 43 for homework tonight. Nailed it. Have a great day, everybody. Thank you for the treats. Well, I was pointing at that general table. Bye, guys.